To those of you in the northern hemisphere where it's currently winter, I envy you. It's about 30 degrees in the office, but the ray tracing series must go on. Hey, so guys, my name is Cherno. Welcome back to the new year, to the ray tracing series. We're gonna have a bit of a chill episode today. We're just gonna talk about some kind of performance optimization things, and more importantly, answering the question of how do I find out what the bottleneck is? How do I find the slow part? So last episode, we talked about multi-threading. What we did is we took our currently running code and we made it scale across all of the CPU cores we have available to us. We did that using this kind of STD for each function with the parallel execution policy, and we even have a little define here that lets us kind of toggle that on and off. And our performance with that running, with the multi-threading, was around like 26 or so milliseconds per frame on my laptop, which for reference is running an AMD Ryzen 9 5900HX CPU. And you can see all of the cores here being fully saturated. Now, it doesn't take a genius to see that a performance of like 26 to like 30 or so milliseconds using that many threads and that many cores versus, if I just shut off multi-threading, versus about 60 milliseconds, like, you know, that's about twice as fast, maybe a little bit more than twice as fast, which doesn't really make sense when you take a look at what this looks like. Like, the CPU is mostly idle, so how does throwing that much more hardware at it result in such an incremental performance boost? I mean, it's not that incremental. Twice as fast is still good, but it's definitely not like 8 times as fast, which is something that I would kind of expect. What's interesting as well is that if we actually take a look at our code, the part that we are specifically interested in measuring the performance for and what that timer represents, that's not just one frame of our application. If we actually take a look at walnutapp.cpp here, you'll see that that specific timer, last render time, which let's scroll up over here, that last render, what that actually represents is a timer that we start at the beginning of the render function, and we then get its elapsed milliseconds at the end of the render function. So these three functions are really what we're measuring here. Now, on resize is doing nothing, right? Because there's no resize necessary. So if there's no resize necessary, you can see we have a very kind of early out over here, a very short path, and over here as well, if nothing's changed, we just return. So really it's just this function that we're measuring. And this function consists of what exactly? Well, I mean, a little mem set maybe here, some assignments, that doesn't really count. And then the big kind of meat of it is this kind of for loop. And then we just do set data, which will upload those pixels to the GPU. And then we do some other kind of housekeeping here. So really it's either this function or it's the for loop that's taking up most of the time. So then if it is the for loop, and we do in fact compute it in parallel now, we should expect a rather large increase in performance. And if we don't, then there's probably something else that's stopping us. It's probably another culprit. And specifically with multi-threading, when you go and you take something and you make it multi-threaded and you don't see a huge increase in performance, you can be pretty sure that something inside that multi-threaded code might not be as straightforward and as innocent as it seems. And today what we're going to do is we're going to investigate. We're going to be a bit of a code detective, if you will. It's like I'm making this series for children. I need to find my monocle. Now I'm going to show you guys how we can investigate this a little bit further and figure out what exactly the slow part of this is. But first, I want to thank Brilliant for sponsoring this video and this ray tracing series. Brilliant is an amazing website filled with many courses on various STEM topics. They're a sponsor that's actually really useful for what we're doing here. If you want to learn more about all of the math that goes into ray tracing, Brilliant are one of the best places in the internet to do so, because they have a large number of really high quality, well-made math courses that cover pretty much all of the math that you need for ray tracing. Like for example, their linear algebra course or their calculus course. These are all things that you need to know. And whilst they can be rather complicated topics, Brilliant does a really good job at simplifying them and presenting them in such an easy to follow way with all of these like widgets you can play with to visualize how the math is actually working. They'll quiz you after each lesson to make sure that you're actually learning the content. And they've packaged up these classes into just really bite-sized consumable chunks. If you just have 15 minutes at the end of the day, you can progress. You can learn. Another amazing thing is that you can get started for free. Just go to brilliant.org/thecherno, link will be in the description below, and check it out for yourself. See if you like it. And if you do, Brilliant have been nice enough to offer the first 200 of my subscribers 20% off an annual membership. Huge thank you as always to Brilliant for sponsoring this video. So now that we have our detective hat on, let's see what we can do. So one of the things with optimization that's really important is you have to fundamentally understand what what is going on. If you're not sure what your code is doing exactly, and that also applies to like, distributing your code across cores as well. If you're not sure exactly what your code is doing, then this is going to be much harder and possibly a bit of a waste. What I'm talking about is if we just scroll down here so I can draw, we know ultimately that ray tracing is kind of just a bunch of math. What we're really doing, like if this little box here is all of the kind of code that has to run for one frame to render a frame, we know that most of it is just kind of all of these mathematical equations. We also know that these mathematical equations have to largely most of them have to be done per pixel that we're rendering. What that means is that if we have an image that's say 1920 by 1080, we know that that is about 2 million or so pixels. So we know that we have to go through this math 2 million times. Now again, this might not be all of the math. If we hit if we don't hit anything, for example, then we just go to that miss function and we just return the sky color. That's pretty easy. And on the other side of the spectrum, if we actually hit say this sphere and then we bounce and we hit this sphere and we go somewhere else, then obviously we have to do a little bit more math because that kind of bounce rate is going to intersect with something else, which means we have to run through that math again. So the amount of math that we do per pixel actually will vary. But the point is, when you have math that needs to be done many times and it's not dependent on each other, that is a really good kind of candidate for optimization via multi-threading. Because since there's no kind of dependency, they just all need to be done at the end of the frame so that you can present your image, you can dispatch them across really any number of threads. And we kind of talked about this in the last multi-threading episode. This is more of a recap. I don't want to go too deep into that. If you haven't checked out that video though, I highly recommend you do. It's also why we can, for example, dispatch this on the GPU and it's going to be much faster because the GPU will have thousands of cores, not just 8 or 16 or 32 or whatever. And this, as you can see, is a very good candidate for parallelization. Now, why am I talking about this? We've already done it. Why am I talking about this? Because it's important for us to understand exactly what we've done. If we know that we have all this math to do and it's so easily divisible into so many cores, then we know that if the math itself is the thing that is taking up the most time, and we suddenly go ahead and we basically reduce that, let's just say we decide for now we'll make 4 threads, right? If the math takes, as it did, about 60 milliseconds per frame, and we decide that, you know what, let's split this up into 4 cores. What does that mean? That means that each core is now responsible for 4 times less math, because we've taken that entire mass of math that we have to do, and we've divided it across 4 different cores. It's kind of I don't know, maybe you're at a party and you need to I don't know, put some plates down at the table. There's 100 guests and you have to put 100 plates down. If you get 3 of your friends to help you out, then you can just give them 25 plates each and you'll each hand out 25 plates. You've reduced that kind of work by 4 times. You now have 25 plates to place rather than 100. Each of you have 25 and you can of course do that simultaneously as long as you don't crash into each other. So that's basically the same thing as what we've done here. By enrolling 4 cores total instead of 1, we've gone ahead and we've taken the 60 milliseconds worth of math, supposedly, and we've kind of divided it by 4. And 60 divided by 4, of course, is 15. So what we kind of would expect is that each one of those threads should take 15 milliseconds now, because they have a quarter of this work that is 60 milliseconds. And because they're running concurrently at the same time, that total operation now should take 15 milliseconds and not 60. Now, what we are seeing is a lot more than 4 cores. We're throwing 8 cores and 16 kind of threads at it. So if we have 8 cores, we've thrown twice as much into this. So again, you can probably take that 15 divided by 2 and you get about 7.5 milliseconds or so. And again, technically even faster if we take advantage of the other kind of hyper-threading situation that we have. So then when we see something that is between 26 and 30, that should raise some eyebrows. And I'm kind of going through this the long way. There's obviously a much easier way. If this was a speed run to get from having this problem to solution, I probably wouldn't go down this much thought. But again, I'm kind of using this as a bit of a teaching example, just so that you understand what's going on and why these numbers don't look reasonable. Now, when you see something like this, the first thing that I would think of is that this is not as independent as it looks. So we know that theoretically, this math should not have any dependency on the other math that's occurring. What I mean is 1 pixel that we're processing should not be dependent on another pixel. But these numbers are telling me that there might actually be some kind of link between them, some kind of dependency between them that's actually slowing this down. Now, the most common thing I can probably think of is restricting access to a particular resource. So sometimes when you have something that is needed by all of these cores, probably should have picked a different color like red, this kind of resource, we'll say, that's needed by all of these cores means that when one of these instructions from these cores actually requests this, a number of different things can happen, such as, for example, a lock. And when a lock happens, it means that until this core has received its answer and it's got its results, it's got whatever it needs from that resource, nothing else can continue. Everything else has to wait, because if they're all kind of waiting on that resource and then one of the cores has locked it, then that means that that's it. Everything kind of stalls until it unlocks it, and then the next core, kind of one at a time, can actually go there. It's kind of like if a bunch of people have to enter or leave a stadium and there's just kind of one doorway and you have to all get checked by the security guard, so it's like single file. You might have like so many people that can obviously move around the stadium at once and everything's fast, but as soon as they have to get through that doorway, they have to go single file and they get checked one at a time. It's kind of the same thing. I think my camera's about to overheat. We better hurry this up. And I hope it makes sense why I'm saying that that's one of the most likely candidates, because again, theoretically speaking, if we truly have a bunch of independent math that needs to be done, like CPUs exist to do math, right? CPU cores, they each can do math. There's no restrictions there. If you have data flowing in and out and you have 4 of those cores, you do math 4 times faster. It's that simple, because everything you need to compute that particular thing is contained like within that core, and it's happy to just get to work. What starts to become an issue is when you have to communicate, say, to and from memory, and it's some kind of like shared memory that may need to be locked in some way, and like the kind of access to it has to be, restricted. But if you kind of BYO data and you output to something that is also not kind of potentially locked for writing, then that's it. You just flow through very quickly. Nothing gets in your way. So that being said, where could the culprit be? Now, we could go through all of this code, and try and work out what it is that we're doing that is a little bit suspicious. But of course, there's a much easier way. And that is, why don't we just let like a profiler do that for us? Because what a profiler will do, and specifically just, a normal sampling kind of profiler, we don't need like any instrumentation or anything too deep here, but just a normal sampling profiler, what it will do is it will collect samples throughout our entire application. And by samples, what I mean is it will more or less just ask the program, hey, where are you currently? And it will do that a lot. And obviously, if we're inside a function, say per pixel, and we're spending a lot of time here, if I asked you uniformly over the course of 1 second, if I ask you 1,000 times where you are, and like 90% of the time, 900 times, you tell me I'm inside the per pixel function, then I know that out of that 1 second, you spend this much time in per pixel. And if I increase the number of times I ask you, so I increase the sampling frequency, I'll get more detailed results. And if I decrease it, I'll get less detailed results, and it will just show me like an overall picture. So that's kind of how a sampling profiler works. And Visual Studio has one built in. If we just go to debug and then performance profiler, and we select CPU usage over here and just hit start, what it will do is it will launch. Make sure you're in release mode for this. That will give you much better results. Now, at the moment, we are kind of running in that not multi-threaded mode. So actually what I want to do before we do that, we can take a look at it now, but it makes more sense to do it in that kind of multi-threaded version because it will really highlight exactly what's wrong. So if I go ahead and rebuild that, and now I'll go to debug performance profiler and start. You can also go relaunch performance profiler. So about 27 or so milliseconds, I'll let it run for like a few seconds, and then I'll just hit the close button. That will automatically kind of stop this diagnostic session and read the profiling data for us. And here we go. So we have the very start of the application where it just kind of starts up. That's kind of boring. What we can actually do is we can kind of select a region here that we know is like the part we want to focus on. These are the samples we're interested in taking a look at. And then you can see, well, you can see immediately where the problem is. And we have like this hot path over here. But you can, there's a bunch of different ways you can investigate this. You can go into, for example, this kind of open details over here, and then there's a bunch of different ways you can look at this. One of my favorites, and what I think is probably the most useful, is this call tree. What you can do here is you can just press this like expand hot path a few times, and it will just show you exactly where most of the samples were recorded. So we ran this for, I don't know, like 5 or 6 seconds or so. You can see we collected 58,000 samples, and all this tells us is the distribution of those samples. So we know that out of like 100% of the samples, you know, 52,000 of them, 90% of them were spent inside like this SCD run available chunked work, which is almost certainly part of our kind of for each loop. Okay, we kind of expect that. Per pixel makes up for 74% of those samples, which again makes sense. That's mostly what we're doing. Now, here is where it gets interesting. Random float makes up for 52% of the samples. So 30,000 of those samples were recorded inside this function. That means that this function accounts for 52% of our total kind of usage. That is seeming pretty extreme. And if we actually go into here a little bit further, now we can double click on this at any time and it will show us the actual code. And what's cool about this is it shows us like exactly how long kind of each line of code takes and where the samples were recorded. If we go back to per pixel, in fact, we'll see a bit more detail. You can see that for this entire per pixel function, which is where we know all of the math takes place, right? That's like what we drew there. That is the per pixel function that will be called per pixel. We can see exactly that, like the complete distribution of how long stuff takes, which is really cool. Now, again, this is a sampling profiler, so sometimes like it would be more beneficial and more accurate for you to actually up your samples. I think we were doing, it says here 1,000 samples per second. You can change that to say 10,000 and you'll get much more detail at the expense of potentially slowing down the program a bit. But you can actually see here with varying kind of degrees of red intensity here where like the slow parts kind of are. And obviously the overwhelming slow part in this entire function is this 53% over here, which is ray direction equals this kind of reflect. Now, if you actually follow this along, it's kind of this whole section here, because we know that it's specifically going to be this. It's not the actual reflection, and we know this just by looking at this call stack a little bit more closely. We know that it's going to be random float. Now, interestingly, there's also this self CPU. So Visual Studio actually does a pretty good job at explaining this. If you just hover your mouse over this, it says CPU time spent executing code in this function, excluding time in functions called by this function. So what that means is stuff that is actually happening in that function itself is not taking up much time at all. But it must call a function that does take up a lot more time. And specifically, you can see it calls this. So inside that random function, when we actually do sdistribution, sRandomEngine, this is taking up a lot of time. So we know that generating random numbers for some reason is taking up a lot of time. Now, if we double click on this to view it in a little bit more detail. All right, well, my camera overheated and died, so this is like a week later. Now, where were we? Yeah, so we're inside the random number generator and we can see that get bits is exceptionally hot, like 49%, 28,000 samples inside get bits. Now, if we go down the rabbit hole a little bit, we need to figure out what exactly get bits is. So get bits is a function. I'm inside like the X utility header. By the way, this may be different depending on what like platform and compiler you're using. I'm using MSVC, of course, in Visual Studio on Windows. So that's why if you look at the location of this header file, you can see it's inside that MSVC compiler. The implementation that you're using may, of course, vary. So if we scroll down a little bit, we can see the implementation of getBits over here. Now, the main thing that it's doing, apart from just like, you know, trying to find a value within the range and eventually returning it, is calling this like ref thing, which looks like a function, but actually you can see it's a reference to urng, which is a class. So this is actually the kind of call operator on that class. So this is actually calling a function inside this class. And what is this exactly? Well, it's like the template argument for this. So to see what this actually is, we kind of have to do a little bit of digging. If we go into Walnut, this is becoming like a, really are going down the rabbit hole. We can see we're using a random engine here called MT19937. And if we look at that, you can see it's the Mersenne twister engine. This is actually the kind of like pseudo-random number generator we're actually using. If we take a look at the implementation of that, and you can see it has a base class over here, you'll eventually see that we find this call operator over here. So this is the function that's actually being called from getBits. This is supposedly the slow part. And if you don't have much experience with this kind of thing, it can be a little bit difficult to actually see what the issue is here. Because if you take a look at this function, there's nothing really that suspicious there. I mean, we have like refill upper and refill lower, which does like what seems like a bunch of math. Most of it's behind like an if context spur, so this stuff gets kind of compiled out potentially. But then all we're kind of doing here is seemingly accessing some kind of array. So we have some kind of state that's actually part of this class. And then we're doing like some exclusive ORs, like some bit operations, basically shifting left, right, you know, anding, that kind of stuff. Now, the issue here is that it is in fact true that most random number generators have some kind of state. They hold some kind of state, and you can see it really clearly over here. We have an entire array of state whose index gets incremented. The index we access it at gets incremented every single time we call this function. And this is obviously very important, this value that we're retrieving from that state, because what we're doing is then doing a bunch of operations with that value that we need to retrieve. And this state itself, whilst we're not actually writing to it from within this function, refill upper and refill lower, if we scroll down a little bit, you can see we are in fact writing to that state. Now, ordinarily, that's fine. What's wrong with doing that? Nothing. However, this is no ordinary use case. What we're doing is using this exact state, this single instance of this state, across every single core and thread on our CPU. And what did I say earlier in the video? One of the most common reasons that we'll have some kind of slow bottleneck here is because we have some kind of resource. We have some kind of resource here that's being accessed by many different accessors, like many different threads essentially are accessing this one resource. And what does that require? That requires some kind of resource management. Now, in this case, there's no lock on it. There's no mutex. There's no there's no spin lock. It's not gonna wait until it gets access to it. However, because we have so many threads, and don't forget, this CPU that I'm using here has 8 cores and 16 kind of hyper threads, which is part of something called SMT, simultaneous multi-threading. We're not gonna discuss like CPU architecture here just yet, but basically if we have like 8 or 16 or whatever cores trying to read and write from this single array of memory, how do you suppose that's going to work? Well, first of all, ignoring any potential errors we might actually experience from that, the real problem here that's actually causing this slow performance is because all of the CPU cache across all of these cores has to be invalidated whenever we reach for this variable. What would usually happen if we were accessing this from just one core is this kind of array would be very happily sitting inside our CPU cache, and it'd be fast to read, it would be fast to write, everything would be wonderful. However, since we have so many threads attacking this memory, it has no choice but to kind of flush that CPU cache and retrieve the value again. Now, technically, we do have a shared cache between cores. L3 cache is usually shared, so it's probably not quite as bad as like an entirely cold memory read from RAM. However, the individual cache that lies inside each CPU core cannot possibly contain this value, because other cores are also modifying it. Now, this is actually a really, really interesting topic, and to be honest, I'm considering making a video just talking about this and writing some code that will demonstrate more clearly what is actually happening here. But long story short, in this ray tracing series, let's just cut to the solution. How do we fix this problem? Well, the simplest fix, the easiest thing that we can do is just to say, why on earth would we have 16 threads all sharing this kind of single random number generator state if we can just get each core that needs to generate random numbers to have its own random number generator state? So in other words, if each core, if each thread was just to have its own instance of this random number generator engine, then we wouldn't have this issue, because the state is going to be local to that core, the state is going to be inside the CPU cache, and this will be miles faster. So how do we do that in a simple way? Well, if we go back to like our renderer, what we could do is just say, if we know that we have like, I don't know, 8 threads, we could just create 8 versions of this kind of random engine here. If we had 8 instances of that we kind of manually created and we assigned one per core, then that would be totally fine. However, we're kind of dispatching these using std for each. So there's like, even though we could technically get like the thread ID and do all of this kind of manual stuff behind the scenes, there's actually a much simpler way to make this work. And that is, all we need to do is, if we go to the random class over here where we actually declare this, we can actually use a keyword called thread_local. And what that will do is basically create an instance of this per thread rather than just one kind of global instance across everything. Now, we also need to make sure that we go to the definition of that. I don't know why the definition is split up. This could have just been inline static, but whatever. If you do have your definition split up like this, then you also have to make sure that you declare it as thread local here in the actual definition. So with that one change, just adding thread local to this sRandom engine, let's see the difference. Wow, look at that. 10 milliseconds. 10 milliseconds per frame. That's a rather big difference. If I get rid of thread local, just so that we can go back and compare it quickly, that was like 30 milliseconds. So that's a huge difference. All because we now have one instance of this per thread, with the main point here being that those CPU cores can actually take advantage of their local cache. And there you go. Amazing. Now, there's lots I could continue talking about here. This is a very deep topic, but I want to kind of wrap this up by just saying this. The main giveaway here that leads right to this being the problem is that back when I talked about every single pixel having all of this independent math to do, it was really easy to see how multi-threading would dramatically speed that up. But what we found is that the calculation for each given pixel was not in fact as innocent as it seemed, in the sense that it was completely independent of anything else. Technically, to work out every actual like closest hit that we had, including like the bounces and everything when we cast a single ray, so for each pixel to calculate its color, we would actually need to have that reflection ray happen, which meant that we needed to generate a random number. And in fact, I think 3 random numbers. If we go back to the renderer quickly, over here inside per pixel, when we actually do this reflect, so if we don't hit anything, we obviously break and we get like the sky color and stuff, but if we do actually hit something, we're kind of in here, and you can see we call walnut random vec3, which calls float 3 times, which gives us 3 random numbers by using that random number engine. And so instead of our pixels being completely independent, they suddenly now had a link between them, because to get those random numbers, we would have to kind of write to and read from a kind of shared state that that single instance of that random number generator actually had. And so suddenly these weren't completely independent operations that each core could actually kind of take charge of. They were now kind of bound by shared memory that had to be somewhat kind of sensibly accessed, right? You had to invalidate the cache, because otherwise, if another core writes to it and you've got something in your local cache, you wouldn't actually see those changes, and that would be wrong. And so by breaking these links and giving each kind of pixel its own random number generator, it sounds crazy, each pixel its own random number generator, but remember, it's because technically that is what's happening. It's not like we're calculating all like 2 million pixels at once. We're handling those pixels by like these 8 cores. So if we give each core its own random number generator, that means at any given time, when the pixels are being calculated simultaneously, they're all accessing their own independent random number generators. And that means that that can be cached like correctly, more effectively, and everything is great. Now, the last thing I want to say is that I did actually create this issue in the ray tracing repository to just ask people about whether or not there would be another kind of faster way to dispatch all the threads we'd need to actually process like the multi-threading. And a lot of you did suggest like some certain things. However, I believe the consensus is that the for each implementation is actually pretty good. So I am still interested if anyone can in fact beat what we've got right here. And inside this very issue is where a lot of people did also point out that the random kind of number generation was the issue, and some thread local random number generators were also kind of a good idea, which is definitely very helpful, even though the issue was mostly about the multi-threading side of things. But nonetheless, it was nice to see the community doing some digging and seeing like what the slow parts of this code actually are. So thank you. Hope you guys enjoyed this video. If you did, please don't forget to hit the like button. As I mentioned, I might make an actual like C++ video discussing like the intricacies of why exactly this was in fact so slow. And that's why this series is just such a great way to kind of dive into C++ and learn about optimization. Ray tracing is just a great candidate for this kind of stuff. Don't forget to check out Brilliant using my link in the description below, and I will see you guys next time. Goodbye.